In thermodynamics, entropy is a measure of the number of specific realizations or microstates that may realize a thermodynamic system in a defined state specified by macroscopic variables. Entropy is commonly understood as a measure of molecular disorder within a macroscopic system. According to the second law of thermodynamics, the entropy of an isolated system never decreases. Such a system spontaneously evolves towards thermodynamic equilibrium, the state with maximum entropy. Systems that are not isolated may decrease in entropy, provided they increase the entropy of their environment by at least that same amount. Since entropy is a state function, the change in the entropy of a system is the same for any process that goes from a given initial state to a given final state, whether the process is reversible or irreversible. However, irreversible processes increase the combined entropy of the system and its environment. The change in entropy of a system was originally defined for a thermodynamically reversible processes, where T is the absolute temperature of the system, dividing an incremental reversible transfer of heat into that system. The above definition is sometimes called the macroscopic definition of entropy because it can be used without regard to any microscopic description of the contents of a system. The concept of entropy has been found to be generally useful and has several other formulations. Entropy was discovered when it was noticed to be quantity that behaves as a function of state. As a consequence of the second law of thermodynamics, entropy is an extensive property. It has the dimension of energy divided by temperature, which has a unit of joules per Kelvin in the International System of Units. But the entropy of a pure substance is usually given as an intensive property, either entropy per unit mass or entropy per unit amount of substance. The absolute entropy was defined later, using either statistical mechanics or the third law of thermodynamics. In the modern microscopic interpretation of entropy in statistical mechanics, entropy is the amount of additional information needed to specify the exact physical state of a system, given its thermodynamic specification. Understanding the role of thermodynamic entropy in various processes requires an understanding of how and why that information changes as the system evolves from its initial to its final condition. It is often said that entropy is an expression of the disorder, or randomness of a system, or of our lack of information about it. The second law is now often seen as an expression of the fundamental postulate of statistical mechanics through the modern definition of entropy. History. The French mathematician Sadi Carnot proposed in his 1803 paper Fundamental Principles of Equilibrium and Movement that in any machine the accelerations and shocks of the moving parts represent losses of moment of activity. In other words, in any natural process there exists an inherent tendency towards the dissipation of useful energy. Building on this work, in 1824 Lazari's son Sadi Carnot published Reflections on the Motive Power of Fire, which posited that in all heat engines, he made the analogy with that of how water falls in a water wheel. This was an early insight into the second law of thermodynamics. Carnot based his views of heat partially on the early 18th century Newtonian hypothesis that both heat and light were types of indestructible forms of matter, which are attracted and repelled by other matter, and partially on the contemporary views of Count Rumford, who showed that heat could be created by friction as when cannonballs are machined. Carnot reasoned that if the body of the working substance, such as a body of steam, is returned to its original state at the end of a complete engine cycle, that no change occurs in the condition of the working body. The first law of thermodynamics, deduced from the heat-friction experiment Sir James Joule in 1843, expresses the concept of energy and its conservation in all processes. The first law, however, is unable to quantify the effects of friction and dissipation. In the 1850s and 1860s, German physicist Rudolf Clausius objected to the supposition that no change occurs in the working body, and gave this change a mathematical interpretation by questioning the nature of the inherent loss of usable heat when work is done, e.g., heat produced by friction. Clauses described entropy as the transformation content, i.e., dissipative energy use, of a thermodynamic system or working body of chemical species during a change of state. This was in contrast to earlier views, based on the theories of Isaac Newton, that heat was an indestructible particle that had mass. Later, scientists such as Ludwig Boltzmann, Josiah Willard Gibbs, and James Clerk Maxwell gave entropy a statistical basis. In 1877, Boltzmann visualized a probabilistic way to measure the entropy of an ensemble of ideal gas particles, in which he defined entropy to be proportional to the logarithm of the number of microstates such a gas could occupy. Henceforth, the essential problem in statistical thermodynamics, i.e., according to Erwin Schrödinger, has been to determine the distribution of a given amount of energy E over an identical systems. Carathéodory linked entropy with a mathematical definition of irreversibility, in terms of trajectories and integrability.